Assalamu alaikum, Bismillahirrahmanirrahim. This is the first part of the combined lecture for week 2 and 3. The previous one, the sound was unclear, so I'm re-recording it again. So at the beginning, we need to see what are the processes that we can extract the energies from the sun. We can receive it as either solar thermal or heat energy, or we can receive it as the sunlight striking on the photovoltaic panel to produce electricity, which is called the solar photovoltaic energy. Now we are going to see how the energy travels from the sun up to the earth. So earth is located at 1 astronomical unit away from the sun, which in terms of meter will be 1.496 into 10 to the power 11 as we see here. So this one is the earth's location. Earth's outer surface is here, and you can see from the center of the sun the energy is kind of spreading in a divergence manner, right? There's a divergence, a conical shape. So the energy flux is most dense on the sun's surface, starting like we are counting from the sun's surface is 6.33 into 10 to the power 7 watt per meter square. And when this energy flux is traveling up to this distance of 1 astronomical unit, it will be reduced to only 1367 watt per meter square, and this is actually on the outer atmosphere of earth. Okay, now it's time to see what is terrestrial sunlight. Terrestrial sunlight is the sunlight that reaches the Earth's surface after passing through the atmosphere. So outside Earth's atmosphere, intensity is higher than on Earth's surface because the sun has to travel through the surface air, moisture, dust, etc. So it gives a way for the sunlight to get diffused, and some comes in as direct component. We will learn about this diffused and direct radiation later. So if we see that solar energy distribution, right, 45% is in the visible spectrum, 1% is the ultraviolet and X-ray, and 54% is in the infrared region. So we get the idea that this portion most likely will be contributing to the heat energy, right? So now we are going to see, if we look from the earth, if we look at the sun, we will always see it as a small disk, right? Small yellow disk. So that's why we need to count this angle, the angular size, and this one is found to be 9.3 milliradian. If you convert it to degree, it will be 0.5 degree at 1 astronomical unit. Okay, so this apparent size of the sun, it will vary by plus minus 1.7% because of the location of the earth's orbit around the sun. So we know that the orbit is elliptical, so sometimes the earth will be near to the sun, sometimes the earth will be further away from the sun. So this is a representation of how solar energy reaches the earth's surface. So you can see on the way from the 40 kilometer above the earth's atmosphere, um, the solar irradiation that comes in is 100%. Then it is deflected by the ozone for the UV, and then the upper dust layer, air molecules, and then at the near the lower ground there are water vapor clouds, and to the lowest layer it has the dust. So all these layers, they are contributing into the diffused solar irradiation or scattered solar irradiation. So after all these layers, the direct solar irradiation that reaches the earth can vary between 83% to 33% depending on the condition of like clouds, whether there are clouds or moisture in the air, or considering all these things. So it will vary also according to the zone, like the most moist zone will have more diffuse solar irradiation compared to the direct solar irradiation. Next, we are going to see how this direct and diffused solar irradiation can be used. About direct component, this one is available to the highest amount when the day is a clear day. That means no cloud. It's a very sunny day and no moisture. I mean, very little moisture in the environment definitely will provide more direct component that is directly coming from the disk of the sun. So it can reach up to 80 to 90% of the total amount of solar energy reaching the surface of the earth. And this beam component is of great interest because you can produce high temperature from it by concentrating. We will learn about the concentrator in our next chapters, but we can actually concentrate the solar irradiation to produce something of very high temperature. And when we do the concentration, it's more desired to have the direct solar irradiation because it works best. So other than the direct component, on a cloudy day or in a high moisture environment, the type of solar irradiation we are going to see is the diffused or scattered component. It can be diffused or scattered. That's why we can see in the shade. Okay? So it's like the light is deflected from the other sides. So it's we can see it, but we really cannot make very good use of it because it's already diffused, right? So its potential, its energy potential is already low, and it is the result. Why does this diffuse component happen? Because when you are having all this nitrogen, oxygen, water molecules or water droplets or cloudy days, right, dust particles, all this will cause the sunlight to get diffused or scattered. And this diffuse insolation, it cannot be concentrated except only some few cases like flat plate solar collector, and some like you can concentrate, but the temperature range will not go up very high. Now we will talk about how we can measure the solar irradiation and what should be the units. One of the primary instruments to capture solar irradiation is pyranometer or pyranometer. It measures both the direct or beam solar irradiation and the diffuse insolation.
Let's see how the pyranometer captures the solar irradiation. As seen in this diagram, if you see, there is a hemispherical glass shield, and you can see the irradiation is entering through all the directions. So there is sun in the sky and clouds also present. But if we look further, you'll see that if I place the pyranometer at an inclination of angle theta, so we can see the sunlight that is falling on the ground will get reflected and will be captured, right? So the direct beam plus the reflected beam, and which is mostly the diffuse beam also, they're all captured by the pyranometer. So when you are getting the data from pyranometer, it is telling you all possible energy that is entering in at that point. In the next slide, we will see how pyranometer works. Remember the term thermopile. Okay, so thermopile is combination of different sensors to measure the solar irradiation and represent it in a term of a unit that is called the energy incoming per unit area, watt per meter square usually. So this thermopile pyranometer, it consists of a thin blackened absorbing surface shielded from the convective loss and insulated against conductive losses. Okay, that's why we place it underneath the glass hemisphere. So when placed in the sun, the surface attains a temperature because it's, first of all, it's black, so it's absorbing, and it is attaining this temperature proportional to the amount of radiant energy falling on it, and this temperature is measured and converted through the accurate calibration into a readout of the total insolation falling on the absorbing surface. A properly designed instrument measures the radiation in all wavelengths and its response to beam radiation should proportional to the cosine of the angle between the sun and a line normal to the pyranometer absorber surface. So about this cosine angle, we will learn later about it in details. Let's have a look in the next slide. Simple drawing, through a simple drawing, how this thing is capturing the sunlight. Now we are going to see through this diagram how the pyranometer works. As you can see that these are all part of the thermopile sensor. It consists of that black surface, and beneath of the black surface we have the voltage measurement devices and thermocouples, while the whole thing is covered by a glass dome. Okay, this one is made up of glass. And why it's particularly glass? Because glass is opaque to infrared rays. So that means this glass dome will only allow the light to pass through, but it will be rejecting the heat wave that's coming along with the light wave. Beside that, this glass dome will give protection to the thermopile sensor inside, and in some cases sometimes they use like a double layer of this glass dome also. So does it mean that we can only measure the overall global solar irradiation, or are we able to measure something that is direct irradiation? Because direct irradiation is very important for solar energy research. Most of the energy we can capture is from the direct solar irradiation. So yes, there is something called the perheliometer, is a device that used for measuring the direct solar irradiation or the beam. Okay, we call direct irradiation or the beam radiation. And this one is it looks like a small telescope, and through this small telescope there is a small hole through which the sunlight will enter. Maybe I go to the next slide and show you how does it work. So you can see the telescope like feature here, and there is a small hole. So we target and align this small hole to capture the solar irradiation that is incoming. So it is directly facing the sun's face here, and there is a usually this angle is like 5 degrees. So the solar irradiation falling on here, there is a protective lens also, and this is a hollow tube. This is a hollow tube, so it will go into this acceptance angle is up to 5 degrees. Then they will come in, and similar to the pyranometer there is a black body and the thermocouple settings. So we are capturing the normally incident solar irradiation through it. So it actually can give us a measure about the direct solar irradiation. Remember when we were talking about terrestrial sunlight, the angular size of solar disk was found to be 9.3 milliradian, which is approximately like zero 0.5 degree or half degree from limb to limb. And I have mentioned that there is a 5 degree aperture or opening for the perheliometer. So due to this variation, there is scope for something called circumsolar radiation to enter. So the perheliometer, although it's supposed to give us the direct radiation only, but due to this aperture angle allowance, there will be some mixture of the circumsolar component. Circumsolar component is the other irradiation component, not the direct one. And it becomes significant when the atmosphere is loaded with aerosol particles like water vapor or cloud. But it's almost impossible to make a perheliometer with only 1 degree aperture, right? It's very difficult. So we do allow that 5 degree acceptance angle as long as we do not really need extremely accurate measurement. The sun is basically a nuclear fusion reactor that has been burning for million years, and most probably it will be burning for a few million years. in future. So this energy has been coming to Earth since the beginning of creation, and we are going to now talk about what type of irradiances that we classify. Okay, so let's have a look into the solar irradiation that is reaching on the Earth's upper surface before penetrating through the atmospheric air and clouds and whatnot, all the particles, everything. So the solar energy is called solar constant, that has a value of 1367 watt per meter square, and that one is located at the top of the Earth's atmosphere. Then the energy further travels through the Earth's atmosphere, the air, water particle, moisture, dust. It gets absorbed, reflected, and it has been found that when it reaches sea level, the maximum it can become is 1000 watt per meter square. So there is a 367 watt per meter square drop between this 40 kilometer of the length above the sea level up to the upper atmosphere. And the amount of solar power available per unit area, like I have been speaking about this watt per meter square, it indicates in 1 meter square of area. If I draw a 1 meter square of area, how much solar energy is entering. So this one is measured in watt, and if you want you can measure it in joules also. In that case you need to record the time, and over the area, watt per meter square. So this one is called as irradiance or insolation. Remember, solar constant is the higher value, 1367 watt per meter square, and the one sun. Okay, whenever you hear this word one sun, it indicates that it will have a value of irradiance value of 1000 watt per meter square. This is the summary of what we have learned so far, the summary of solar parameters. Irradiance is indicated by G or I. G is for the constant properties and I is for any general irradiance that we are measuring at any surface of the earth with different values other than one sun. And it is measured in either kilowatt per meter square, watt per meter square, milliwatt per centimeter square. That's the most used energy unit. Some people do it like kilowatt hour. Some would like to calculate in kilojoule or megajoule. And the measuring device we have learned is mostly two types: pyranometer to capture the global irradiation, and perheliometer to capture the direct solar irradiation. And solar constant, the sun's irradiance that is reaching the outer surface of Earth, is indicated by GSC. It has a value of 1367 watt per meter square. Peak value at sea level, the maximum solar irradiation that can reach up to the sea level, is called called one sun, indicated by G naught. 1 kilowatt per meter square converted to watt becomes 1000 watt per meter square, and 100 milliwatt per centimeter square when you want to measure it in milliwatt and centimeter scale. And the nominal value will be somewhere around 800 watt per meter square. Okay, 800 watt per meter square. It's compared to Malaysia, it's a good value. It's a good value. If you can get the 800 watt per meter square for the whole day, it's quite good. But in Malaysia, we are receiving starting from 200 to like 600, 700 maximum.
Now we will learn about some important parameters in solar irradiation measurement. One is the irradiation, okay, overall irradiation that indicates the total amount of energy coming per unit area, usually per meter square, received over a given period. It can be per 1 hour or it can be for daily, monthly or annually, because we need to know that for how long the solar energy is entering. Definitely at night there is no solar energy. So per day, if I consider it to be a 24-hour day, in that case I'll be able to know including the day and night, total how much of solar energy has entered per meter square area. Another important factor is peak sun hour, which is in short, it's called as PSH. So this PSH is the number of hours for which the solar irradiation is reaching at the rate of 1 kilowatt per meter square, and 1 kilowatt is considered as the one sun, right? We have seen in the previous slide 1 kilowatt is one sun. So for how many hours and how do we measure it, we are going to see in the next slide. Now we will have a look at how is peak sun hour or PSH calculated. Sunlight intensity will definitely change from morning up until the sunset time, right? So you can see that it's like increasing, reaching a very high value, more than even 1 kilowatt per meter square. Then it's reaching to a zero value around the sunset time. So since it is varying throughout the day, instead of adding up every hour of sunlight, we convert it into the number of full sun hour at maximum intensity. So for example, if a location receives 5000 watt hour per meter square of solar energy in a day, we say it has 5 peak sun hour, because 5 kilowatt hour per meter square per day divided by 1 kilowatt per meter square. So PSH is basically the daily solar energy divided by 1000 watt per meter square. So in graphically you can see between 10 a.m. to 2 p.m. we try to draw a block of 1 kilowatt hour 1 kilowatt meter square, and then we try to like normalize this extra amount into this, then we can get there is a like 4 hour of PSH. So we have been talking about the kilowatt per meter square or kilowatt hour per meter square. As per the SI unit, the solar energy is considered in joules. But joule is relatively a small quantity because the sunlight coming in is in large energy quantities. So we often convert it into megajoule instead of joules. So if the solar irradiation energy on a horizontal surface for the whole day is 25 megajoule per meter square, then we must work out the number of hours for which radiation at the rate of 1 kilowatt per meter square would result in the same overall energy gain for that day. Okay, so in the next slide we're going to see what happens and how do we calculate it. First, we try to find the relationship between the kilowatt hour and megajoule. So 1 kilowatt hour means supplying 1 kilowatt energy for 1 hour, which is 3600 seconds, and the watt is basically joule per second, right? Because watt is joule per second. So when you multiply it with the seconds, you'll get the joules. So 1000 watt is 1 kilowatt multiplied by 3600 second gives us 3.6 megajoule. So now we know that 1 kilowatt hour is 3.6 megajoule, or 1 megajoule is 1 over 3.6 kilowatt hour. So that means we have this 25 megajoule per meter square. In terms of kilowatt hour, it will be 6.94 kilowatt hour per meter square, right? So it means in 1 hour, radiation at 1 kilowatt meter square delivers 1 kilowatt hour of energy, and for 6.94 kilowatt hour per meter square indicates that it is supplying energy for 6.94 hours at a value of 1 kilowatt in 1 meter square, right? So the PSH is 6.94. Why PSH is so important, right? Why do we need to know that? Because okay, say for example you want to install some solar panel in an area, you need to know like how much is the solar intensity and what is your energy demand for the house, and in terms of your energy demand and your solar intensity in that area, how many solar panel you need to install. Okay, so it actually gives us a quick idea, quick estimate on the required number of solar panel. So panels required can be found from this following formula. the daily energy demand in kilowatt or watt hour. Panel rating, I mean each panel is capable of producing how much power in watts. Usually solar panels are rated in watts, 100 watts, 400 watts, like that, multiplied by peak solar hour and the efficiency of the solar panel. Okay. Now for theoretically they have considered the efficiency is 0.8. Actually for solar panel efficiency is always below 20%, which is 0.2. So anyway, it's just an example. So if you have an efficiency of 0.8, your peak sun hour, peak solar hour is like 5 hour. That means you're receiving for 5 hour at 1 kilowatt per meter square, and your load, required load, is 3000 watt hour per day or 3 kilowatt hour per day. And you want to know how many panel you want to install, so you can use this formula. So we can see its energy per panel is 1.2 kilowatt hour per day. In terms of that, to serve for 3 kilowatt hour or 3000 watt hour, we need 3 panels.